Hi everyone, and welcome to the fourth and final lecture of this mini course in moduli space of Riemann surfaces. Please, Danilo, go ahead.
Yeah, thank you very much. So yesterday we saw the toolbox that we needed to compute in the cohomology of MGM bar. So this I tried to collect for you the main things that you need to know in order to be able to perform computations. Maybe we can record a little bit what we have seen yesterday. Um, so first of all, we have projection formula. That's very important. Projection formula tells you that the push forward of alpha times the pullback of some other class beta is equal to the push forward of alpha times beta. And that's very useful to pass from MGN bar to MGN plus one bar and vice versa. And this is especially useful to deal with kappa classes because kappa classes are defined as push forwards. Then we have seen the pullbacks of our protagonists, if you remember the psi and the kappa classes. And they are indeed just psi and kappa classes minus a correction. And we saw in which sense the correction was making sense and how to use it. And then we have some considerations about pullback, push forwards, VSL constraints, and some initial data that you need to know because using string dilaton and other equation, you may reduce yourself to the case in which n is equal to 1 or the genus is 0. And then when you reduced everything you could reduce, at the end, you need to use some initial data to finalize the computation. And then we've seen some examples of how to compute the integral of kappa 1 to the power 2. You have to use basically most of the tricks we've seen. So this is a good example of how to do it. Because if you can do this computation, then you should be comfortable with most of the tricks. And when you are comfortable with most of the tricks, you can do most of the calculations. And then here, I wrote that now you have everything to compute. Now you're experts in the computation, in computing in the cohomology of MGM bar. Of course, when G and N are not very small, then even if you can do the computations because you know all the tools and you can apply them properly, it may be still a very long process, right? Like diagonalize a huge matrix. Of course, you know all the steps, but it just takes a lot of time. And the reason behind this is that the number of stable graphs is huge. It grows like 6g minus 6 plus 2n double factorial. So as soon as g and n are not very, very small, the number of stable graphs you need to take into account is just becomes very fast unmanageable by hand. And that's why I suggested many times that you try to use this ADM cycle package that was built on purpose for this kind of calculations. And you can access ADM cycles through any sort of electronic calculus sheet like Cocalc, for example, uh, which is Sage Math based. So you can just access for free Cocalc and initiate some Sage Math sheet and then call ADM cycles from there. But even with a computer, let me tell you that even with a computer, you cannot do very big G and even I would say that even the computer stops very quickly because the number of graphs grows so fast that by hand you usually try to do computations in genus 0 and genus 1 for very small n. And with a computer, you may be able to do computations in genus 2, 3, sometimes genus 4, and still quite small n. So it's not that you can go very far. But usually this is enough to test conjectures. I mean, if a conjecture is true in genus zero, then usually you don't trust it because genus zero is very special, right? And some conjectures may still be true in genus zero, one, and finally you may see something very non-trivial in genus two. But for example, it happened to me personally that with a collaborator, we believed a conjecture because we tested it in genus 0, 1, 2, and some examples in genus 3. And eventually the conjecture was false because but it started being false in some examples in genus 3. So you never know. You really need to test as much as you can and modulate specific curves. But I would say that if something is true in genus maybe 2 or 3, then I mean it's reasonable. Let's say it's reasonable. But still, I mean the computer can definitely allow for some tests that would be completely unreasonable to do by hand. So it's a very good tool to have. It's not a proof, of course. You may still have instances of conjectures like the one I encountered that starts failing at some point. But I would say if you can test it in genus 2 and 3 and it holds, then it's reasonable. Then I gave some exercises because, as usual, the best way to learn to do things is when you do them yourself. It's really not the same thing as just reading the solution. You should just face the sort of difficulty, the pain, and it's really like some linear algebra. I mean, after you do some of these exercises, for example, you can compute the integral of kappa 1 on M04 and the integral of kappa 1 times size 5 on M05, or the integral of kappa 1 to the power 3. That's a longer one, of course, on M06 bar. I mean, after you do some of these exercises, then you just get the gist of it and then becomes sort of automatic. Yeah, so I think this is a kind of exercise that you may want to do until you get bored. When it starts being boring, then you've done enough. And then I have some more theoretical exercises. So, for example, in genus 0, we know very well what the answer is for integrals of psi classes. We take just the integration over M0 n bar of your favorite monomial in psi classes. So psi 1 to the power d1, psi 2 to the power d2, up to psi n to the power dn. We know very well that the answer to this question is the multinomial where you have n minus 3 above and the di's below. Of course, the di's sum up to n minus 3, but you know this from the fact that the genus is 0. Because, of course, the sum of the di's should sum up to the dimension of the space. And so the dimension of the space is 3g minus 3 plus n, but in this case, it's just n minus 3. And then, yeah, the other nice thing is to collect these numbers into generating series. That's something that people often do. And then you can form this big A, G, N of x1, xn. And you can define those as the sum over d1, dn of the integral over mgn bar of some monomial and psi classes. And every time you use some theoretical outside and some power, then you just match that, or you pair them up with some variable xi to the same power. And so now you want to know what this AGN is in terms of these xi's, right? If you can express the generating series in xi's, then in a closed form, then you know all of these numbers. And of course, in genus 0, you have the answer, because in genus 0, the integral over psi of psi classes over M0 n bar is just the multinomial number. And so now if you plug this multinomial number here in genus 0, so pretend g is equal to 0, then of course by Newton's theorem or binomial theorem, But in the multinomial case, then you get that this is just the sum of the xi's to the power n minus 3, right? Because you have n minus 3 here. So you have the sum of the xi's to the power n minus 3. And I want to indicate this sum of the xi's with E1. E1 meaning the first elementary symmetric polynomial in the xi's. And we know from Galois theory or from Viet formula, these polynomials, these symmetric polynomials, they're very well known. There are 6 fundamental bases of symmetric polynomials. And this is the one that is used the most in Galois theory or something like that. Then you have the symmetric monomials. Then you have the complete homogeneous polynomials. Then you have the Schur function. And there is another one that I always forget because it's called the forgotten monomials on the MacBook, on the McDonald book. You have this, the last one is this F that is referred to as the forgotten monomials, symmetric monomials. And indeed, people often forget about them, but these EIs are very much used, and I want to now use E1 instead of writing the sum of the xi's, and I'm doing that for a reason, because it turns out that when you try to extend this formula for genus 0 to higher genera, these guys, these EKs, are precisely the type of polynomials that you like to try to extend this formula in higher genera. And indeed, the next exercise that I would suggest is precisely this one. So if now the genus is not 0, but it's just 1, so the next one. Now you want to compute A1n in terms of these variables x's. And this turns out to be equal to 1 over 24, which is not surprising at all because 1 over 24, if you remember, is just the integral over m11. So this is the n equal to 1 case where you only have one psi class, and the answer is 1 over 24. This was in our initial data. Yeah, over here. So integral of m11 of psi 1 is just 1 over 24. And that's the 1 over 24 here. And then you may expect that you have E1 to the n minus 3 as before. But of course, this is no longer n minus 3 because n minus 3 was the dimension, which is 3g minus 3 plus n when the genus is 0. But now the genus is 1. So you may expect that this is n minus 3 plus 3. So that's n. And indeed, you do have this term. So you may initially think that the answer just stops there. It's just 1 over 24 times this guy. But of course, it's more complicated than this because you have more graphs. And so but you can still think that this is the answer to the leading term in some sense. And then again, you have some correction. Now the difficult part, of course, is to compute the correction. And the correction is something like that. So here you have some sum over k from 2 to n. Well, you're excluding 1 because if you plug in 1 here, then you have, then if k is equal to 1, then you have k minus, then you have 1 minus 2, which is minus 1 factorial, it's not defined. But in any case, here you would have E1 times E1 to some power n minus 1. So basically, you can think that, well, of course, you need to make sense of this, but somehow you naively can think that this term here is the k equal to 1 term in this sum. Because indeed, you would have E1 to the power 1 plus n minus 1. So they simplify and they give you this E1 to the power n. But anyways, somehow this correction takes care of terms that have not only E1s, but just other elementary symmetric polynomials. And the answer is that you get all of them up to the nth one, but then you have these coefficients. And so indeed, the answer does not include just E1, but also all the other EKs. But here you can notice something. You can notice that because here you have genus 1, you have just one elementary symmetric polynomial that is not E1. So let us consider the E1s as sort of neutral. They don't play a big role. But let us focus on the elementary symmetric polynomials that are not E1s. Here we only have one of them per summand, so it's linear. It's linear in these EKs, which are with K different from 1. And the fact that it is linear may be related to the fact that here you have genus 1. And indeed, in genus 0, we had none. So that's kind of consistent for the first two cases. And we may wonder whether this is a general phenomenon, whether if we augment the genus here, we put the genus 2, then whether it would be true that we have quadratic expressions in the EKs, right? We may ask ourselves this question. And in fact, this is true. Well, this is open conjecture, but now it's not open anymore. But it's true that AGNs in the axis are, I don't know if you can see the top, maybe I should, okay, are just the sum over K1 up to KL with L greater than 0. And then you have some coefficient that depends on the EKIs, and here you would have some EK1, EK2, EK3 up to EKL. And that's but there's no statement here because the elementary symmetric polynomials are a basis for the symmetric functions, and you know that these are symmetric by definition. So of course you can express them in this way, expanding them in the EKs. That's no statement at all. This is just a tautology. But now the conjecture is that these guys, they stop at G. I mean that you cannot have more than G factors here that are different from index 1. So the worst that you can have here is EK1, EK2, EK3, EKG, and then all of the other ones must be E1s with index 1. So that's the conjecture. That is not a conjecture anymore. Has been proved. And I mean, this is a surprising thing. I mean, we observed that with a computer, and then we started thinking about why that would be true. And the proof actually is, let me say that the proof that we have so far is not completely satisfactory, I would say, because it doesn't really has to do with the geometry. It would be best if you can find some proof that is geometric, that tells us why the genus, that is a very geometric thing, is related to the number of factors, EKs, which are not with index that is not equal to 1. Okay, so then the next exercise that we propose is this exercise 3.5. That is quite a geometric exercise, and basically here it's this exercise is a good excuse to show this beautiful formula due to Mumford that we actually mentioned several times, but we never really showed it in detail. So what we said last time, if you remember, is that in our protagonist, we have psi classes and kappa classes and Poincare duals of stable graphs and lambda classes. But in fact, lambda classes are not really sort of linearly independent or original protagonists, because in some sense, I mean, they are just made out of kappa psi and divisors. And this is not obvious at all. So therefore they are tautological, right? But the fact that they can be expressed in terms of kappa psi and divisors is quite a non-trivial statement, and this was a theorem by Mumford in 1983. But I never actually told you exactly how this formula goes, and so I wrote it here. Here you see that if you form this big lambda of U, and that's defined as lambda 0 plus u times lambda 1 plus u squared times lambda 2 up to u to the power g lambda g. And now this is just the exponent of the sum over m that goes from 1 to infinity of u to the power m times this b. This is a Bernoulli number, so Bernoulli number m plus 1. So if you encountered Bernoulli numbers before, I mean, it's there are nice numbers and they pop up in different contexts, especially in like either Gromov-Witten theory um, or Fock space formalism, and this is not a coincidence. Or, for example, in number theory, when you have this the famous Riemann zeta function, and this is also not a coincidence that it's actually related to what is written here and so on. So they're very nice numbers, and whenever they come out, it's nice to connect different ways of Bernoulli numbers coming up. In this case, actually, the main reason why Bernoulli numbers come up in this formula is because this formula is obtained by the Grothendieck-Riemann-Roch theorem. And whenever you use the Grothendieck-Riemann-Roch theorem, you have to intersect with the Todd class, and the generating series of the Todd class is the generating series for the Bernoulli numbers. That's the main reason. But then it turns out that it's also connected to other things that I mentioned before. Okay, and then after you have, this is just a number, right? So it's not, no classes are mentioned here. And now this is the important part. You have three terms. The first term is a kappa class, or kappa M. This is not surprising, I mean, because you see, how is U inserted in this formula? U is precisely the formal variable that keeps track of the cohomological degree, right? So here you have cohomological degree 0, and you have U to the power 0. You have cohomological degree 1, you have U to the power 1, you have cohomological degree G, and you have, I mean, complex cohomological degree G, and you have U to the power G. So now it's homogeneous, completely homogeneous, right? So you cannot break this rule. If you would break the rule in the right-hand side, it would mean that you have non-trivial relations. So anything that would differ from this principle would imply that you have some non-trivial relation between the coefficients and non-trivial vanishing. But this is not the case, because here you sum over U m, and you have U to the power m, and then you would expect here something that is homogeneous of cohomological degree, complex cohomological degree m. And this is precisely the case, because the first time is kappa m is matching the degree, right? And then you have psi classes again to the power m, because this is already of degree m, but this is of degree 1, complex degree 1. So now you need to take it to the power m in order for it to be homogeneous. And there is no reason to prefer some psi classes instead of others, because this class, let me remind you that this class is just the total Chern class of the Hodge bundle. The Hodge bundle doesn't have anything to do with mark points, so there would be no reason to prefer some mark points with respect to others. So you would expect something symmetric, homogeneous of degree m, and that's exactly what you get with a minus sign. Minus sign is not easily explainable from these considerations, but I mean, it's very natural, and then you expect something that has to do with divisors or with nodes, because the nodes are the main ingredient that would, if you iterate nodes, you're building stable graphs, right? So if you have an operator that pinches a node, that pinches some loop and turn it into a node, then you could apply that several times and create many edges starting from one component, and then you would start subdividing, creating many components, and that's precisely what generates all stable graphs. And indeed, this is precisely this operator J lower star. So J is the boundary morphism. And so now when you consider J lower star of something, you mean that this is the operator that indeed pinches a node, and so it creates an edge in the stable Dewey graph. And because you have exponential, it needs to be interpreted, this exponential here, in the formal power sum sense. So you would take this sum and you would elevate that to the power n divided by n factorial, and you would sum over n from 0 to infinity. Of course, it would stop before infinity because of the dimension of the space. So it would stop at 3g minus 3 plus n. And still you would have a lot of vanishing, because this sum also stops at 3g minus 3 plus n, but depending on the expansion of the exponent, you would have like fewer and fewer terms, the higher n. But anyways, like my point is that because here you have an exponential, then this j is applied several times, not just once. In principle, you could apply it at most 3g minus 3 plus n times, right? And so this creates a node or an edge. And now this part over here tells you that, well, you have two branches of a node, let's say the left side and the right side of the node. And on each of the two, we've seen that if you consider the normalization of the curve, it makes sense that you remember the node with a mark point on that component. And on that mark point, you can have psi classes. So psi prime is the psi class on the left side of the node, and psi double prime is the psi class on the right side, on the right branch of the node. And then you have to insert these minus signs precisely in this way, and then you take those to the power m. But after you've done so, you divide by the sum of psi prime plus psi prime prime. So now you may be worried about this division because you may say, well, this doesn't make sense because I don't know the meaning of dividing by psi classes. And in fact, you don't need to worry because this expression is always divisible. I mean, the numerator is always divisible by the denominator. And you can see that by the usual formula and also by the fact that the Bernoulli numbers, if you know Bernoulli numbers, I mean, you for sure know this property, but Bernoulli numbers, they would vanish whenever the index is odd and is not 1. So Bernoulli 1 is not 0, but Bernoulli 3 is 0, and Bernoulli 5 is 0, and Bernoulli 7 is 0, and so on. So now, if you don't, I mean, you cannot allow this m plus 1 to be odd, meaning that you cannot allow m to be even. And if you're worried about the first Bernoulli number, m1, this, b1, sorry, this only happens whenever m is equal to 0, but m is never 0 because the sum starts from 1. Also, if m would be 0, then you would have problems because now you'd have exponent of u to the power 0 is usually not something that you want because of convergence reasons. And I mean, it's usually you want it to start from some power that is at least 1. Okay, so this term is divisible. M is always odd, so that m plus 1 is always even. So this is odd, and you can always divide. And this division by 2 comes from the automorphism factor. If you remember, whenever you have some self-loop, for example, you would have this 1/2, but now you don't have necessarily a self-loop. You can have an edge. But again, like you want to sort of symmetrize according to the ways that you would have to attach half edges to an edge. So anyways, this is a beautiful formula. It's consistent with the degree. It makes sense, and it only uses tautological things, and that makes this guy tautological as well. And that's usually, I mean, it's really some concrete formula that you can work with. For example, if you would like to compute lambda 0, well, that's clearly equal to 1, right, from this formula, because you don't want powers of u. So now you're forced to take like 0 from here. So I have exponent of 0 is 1. So you can immediately compute lambda 0, and you can also immediately compute lambda 1, for example. Lambda 1 would be obtained by removing this exponential and also selecting m equal to 1 from here. So lambda 1 immediately is just Bernoulli 2 divided by 2. And then you would have kappa 1 minus the sum of the psi classes to the power 1. And here m is equal to 1. So this guy cancels out. So you just have the sum over all possible nodes, all possible ways of splitting your smooth curve with exactly one node. So you either decorate it with kappa 1, or you decorate it with psi classes to the power 1 in all possible ways, or you split it into with a node, or you don't split it in two because it's a non-separating node. And that's really like it's an extremely concrete formula for lambda 1. And now if you're integrating lambda 1 over some mgn bar, you can just use that formula on that mgn bar and really get an answer out of that if gn is reasonably small. Okay. So, well, some of these exercises I've done it for you right now. Prove that only odd nth terms contribute. That depends on the property, on the vanishing property of the Bernoulli numbers. And also, yeah, you want to prove that this big lambda of u to the -1 is equal to lambda of minus b. So this is also a very, very beautiful property, and you don't get this property very often with classes in MGM-Bar. It's a very special thing. And somehow, like, it's beautiful that Mumford formula gives you that for free. Well, first of all, if you have some class in the cohomology of MGM-Bar, it's not a given at all that the fact that you can invert it. Like this is already like something extremely special. But of course, here you see that Mumford formula is an exponential formula, and whenever it's an exponential formula, then it's invertible because the inverse would just be exponent of minus that, right? So it's it's very rare that it's invertible, but here you have an exponential form, so for sure it's invertible. But now it's not a given the fact that the inverse would be expressible again in these terms. But now here you have something very special happening again, because if you want to invert this, you just put a minus sign here. But now you know that Bernoulli numbers with odd indices vanish, so with even m vanish. So now you know that this power is always odd. So now this minus sign that you added to invert it, you can bring it inside the u variable and send u to minus u just because this 1 power m is always odd. So now you can recast this guy, so the inverse of lambda of u, in terms of lambda of minus u. So now you know that lambda of minus u times lambda of u is equal to 1, as in, by 1 I mean the fundamental class, right? Which is just this guy here. And this is extremely special because, well, think about it. This is a degree G class in cohomology, and this is a degree G. And now you're multiplying them, and you're getting something of degree 0. That means that all of the possible combinations of these multiplications that are not of degree 0, they must vanish. So you are getting a nice, very nice list of tautological relations. So let us notice the first one. If you pick the top degree term from here, which is of course lambda g, that's the top you can have here. And here you have also minus lambda g. That should give the degree 2g class from the right-hand side, which is of course 0. So now you're getting that lambda g times lambda g is equal to 0. And this is also an extremely useful relation in the computation modular space of curves. It's something that people use very often. It's very, very precious, this one. Of course, you can prove that independently from geometry without using Mumford relation. But I mean, first you need to prove that lambda g is vanishing either on the compact type compactification or on its complement. This is a statement that you need to prove. And it's quite an serial statement. And well, first you need to introduce the compact type moduli space, which is a partial compactification. So we've seen MGN open the moduli space of smooth curves, and we also saw MGN bar, the Riemann compactification that was achieved by adding nodal curves which were stable. Now this compact type curves, it's something in between. So you do add some nodal curves, but not all. So now the question is, which ones do you add? You add the ones that do not have non-separating nodes. So you don't want non-separating nodes. You want only separating nodes. And now you can prove that lambda g vanishes on that locus, but also on the complement of that locus. And now this implies that lambda g to the power 2 vanishes because you use the first lambda g on that locus, and assuming that it vanishes on the complement, but then now if you intersect again, then you get 0 because you can assume that lambda g is now on the complement where it's already vanishing because of the first lambda g. So you can prove that from the geometry, but you see how nice you get, how nicely you get this relation just from Mumford formula, because you just multiply by a minus, then you notice that you only have all the contributions, and then you get this equation over here. Now this equation over here, you start analyzing it, and you start extracting a lot of relation. And this is just the first one. You have many others, of course. You have you have g of them, or something like that, or g minus 1. I don't know. So the next one, for example, would be that lambda g times lambda g minus 2 is proportional to lambda g minus 1 squared, right? And then you can compute the coefficient of proportionality that is probably 1/2. And you can keep going. You can keep going, and the next one that, well, the last one that you have, the last non-trivial such relations will be the lambda 2 is equal to lambda 1 squared divided by 2. This is also an extremely nice and useful relation to have. This is for all g and n. I'm not restricting for genus 1 or whatever. I mean, in genus 1, this one would be 0, but well, which is consistent with the fact that lambda g squared is 0, right? So you can immediately test this for genus 2. It all makes sense. So this will be the last non-trivial relation that you have, and then you have all of the ones in the middle. So this is also a very good exercise for find explicit relation for lambda 0, lambda 1, lambda 2 in terms of psi, kappa, and graphs for small g and n. Okay, so now let me temporarily interrupt the sharing just because I want to switch to the next set of slides. And now here I would share again the slides and I would give you the answer to this question. Okay, so let me expand on the relations that we mentioned before. Here I wrote lambda of u for u equal to -1. And here I wrote lambda of u for u equal to 1. So we know that for any value of u that is opposite, we're going to get 1 out of this. And indeed, I can pick the value that I want, for example, u equal to 1. So now in degree 0, I get 1 equal to 1, which is not very interesting. For degree 1, I get lambda 1 minus lambda 1 equal to 0. This is also not very interesting. For degree 2, we get lambda 2 minus lambda 1 squared plus lambda 2, that is 0. So that gives us the relation that we want, lambda 2 equal to lambda 1 squared divided by 2. Then in degree 3, again, we get nothing, and you can imagine that this would work in general. For odd degrees, you get nothing. But for even degree, you get like these relations which involves a larger and larger number of lambda classes, but always quadratic terms. So from this relation, you get that lambda 4 plus lambda 2 squared divided by 2 is equal to lambda 1 times lambda 3. And then you can keep going. The last one you would have is this. So basically, this is the one before last. You would get -1 to the power g times lambda g minus 2 plus basically the opposite of that plus lambda g minus 1 squared times -1 to the g minus 1 equal to 0, from which you recover the relation I mentioned earlier, but with the right coefficient. And in general, you would have these nice quadratic lambda relations. These objects are very nice, actually. These lambda classes, I mean, they have been studied a lot. There is this celebrated paper of Faber and Pandavipande, for example, concerning Hodge integrals. Hodge integrals have to do with Cohn-Witten theory. That's why people are interested in them. They are also interesting per se within the theory of moduli space of curves. There are several like other tricks or from geometry, from either like tropical geometry or some other sources of geometry that give you that allow you to compute in closed form some of these Hodge integrals. Their closed formula is still open in general. Like we don't know exactly how to compute. I mean, we know how to compute Hodge integrals by using all the tricks that I showed you. Like you explode each of the lambdas with the Mumford formula, and then very, very patiently you write it as a sum of a huge amount of terms, and then for each of them you either use like string equation or dilaton equation or some Beer-Savart constraint or some projection formula, but it's a very long process. But of course we know how to do it, and computers know how to do it. But closed formula for them in general is still open if they exist. But well, when you don't have a lot of lambdas, we know that we do have closed formula. This was initially related to this lambda G conjecture. Like, for example, if you take the integral over a moduli space of curves of mgn bar of lambda G times a monomial of psi classes, then now we know that this is just connect. It's a very nice answer, actually. This is equal to just the integral over mg1 of lambda G times psi 1 to the top power, so to the maximum amount of psi classes you can have, times some multinomial coefficient. So somehow the answer for generic n can be reduced to the answer for n equal to 1, just in the case that you're intersecting lambda G. And this was known as the lambda G conjecture, and then there were at least like 3 proofs of this, maybe now 4 or 5, I don't know. And then this principle, but this is only with lambda G. I mean, we don't know if we have something similar with some other lambda that is not lambda G. And then the same principle was proved to be true with lambda G times lambda G minus 1, which is also a very particular combination of lambdas because it somehow encodes another partial compactification of this space, which is not the ones that I told you about before. It's not a compact type, but it's a rational type. Rational tails locus of curves, which is a different one. But again, like these are very special cases. I mean, if you give me integrals of lambda 5 times lambda 3 times lambda G minus 4, and you ask me, okay, intersect that with any monomial and psi classes that you like. Is there a nice formula about those numbers? I mean, I have no idea. And I think nobody has an idea. So there is still a lot to explore in terms of Hodge integrals. Then there were very nice papers concerning Hodge integrals and Virasoro constraints for Hodge integrals with 1 lambda. But you may ask yourself what happens with several lambdas. I mean, there are a lot to study, and usually these results are quite complicated to prove, to be honest. So it's still very interesting, and still very much on the boundary of what people don't know and would like to do. And it's also, I would say, it's on the boundary with what we don't know and what we think we then we should be able to achieve. So it's a good area of research. And also, of course, I would love to show you how to prove Stirling equation directly from the geometry of MGM bar, because this is very instructive. I mean, this is a very typical exercise in modular space of curves. It's also done on the limited funky nodes, of course. And it's something, again, one of these computations that you do once, but then it means that you really learned how to use these tricks on modular space of curves. So let me remind you that the Stirling equation is the following equation for integrals of psi classes. So if you're integrating over mgn plus 1, psi 1 to the d1, psi n to the dn, and now you notice that you don't have any power of psi n plus 1. So what you can do is apply Stirling equation, and you get a bunch of integrals of mgn bar instead of mgn plus 1 bar. So you're reducing n by 1, and this is a very useful thing to do. So basically, how do you do this? You just sum overall I from 1 to n. And now, of course, why do you sum? You sum because you need to reduce the total power from this monomial, because otherwise you're going to get 0, right? So the dimension of this space is 1 more than the dimension of this space. Therefore, the degree of this class must be 1 more than the degree of this class. So now you want to decrease the power of psi classes by 1. But how do you decide in which way you're allowed to do it, right? Because why would you prefer removing powers of psi 1 rather than removing powers of psi 2? There is no reason to prefer one mark point instead of another one. And we know that overall this computation must be symmetric under permutation of mark points. So now a reasonable answer would be to remove 1 from a power of some psi class, and then to sum over all possible ways of doing that. So symmetrize over this operation. And this just so turns out to be the right answer. So it makes sense, but you can still have some correction. And then you prove this formula and you see that you have no correction. So the initial guess, the most obvious guess in some sense. So I wanted really to convince you that this is the most obvious guess that you can do just because of dimension reason. And then I wanted to stress that there is a good news. The good news is that the most obvious guess is the correct one. This is not always the case, of course. We saw that in different cases before, at least in 4 or 5 cases, we had that the most reasonable answer was correct up to some correction. So the leading term was indeed what you would expect, but then the formula was not correct still because you needed to either add or remove some correction and that you can think of as some sub-leading term. So it's correct up to the leading term, but not completely correct. You need to correct it. But here you don't need to correct anything. It's just correct, straight up. And so how do we actually prove this formula from the geometry? Well, let me remind you that again, the pullback of psi class is the psi class. Well, these two psi classes live on different spaces, of course, because you have this pullback that is connecting mg n plus 1 and mg n bars. And here you do have this correction. If you remember, the correction was that you put all the genus in one component, and now you attach a bubble with 2 mark points. The point I is the index of the psi class you're working with, and n plus 1 is the mark point that you're going to forget. So these are the 2 special points of our computation. This pi knows about the n plus 1. So the task of this pi is to forget about this point. So it knows that n plus 1 is involved in a computation. And this index knows that this mark point is going to be involved. So it makes sense that these 2 play a special role compared to the other ones. And this is indeed the case. Okay, so now let us just remember that x to the power d minus 1 to the power d is this guy. This is the usual things that we study during our bachelor in mathematics. But now you can apply this identity here, and you can apply it to the fact that psi I to the power d minus psi upper star to the power of psi I to the power d. So again, let me stress that these are 2 different classes. Now, because if you remember, the pullback is always a ring isomorphism, but the push forward it's not a ring isomorphism, it's a ring morphism. So it commutes with products, whereas the push forward is not, and it does not commute with product in general. Now you can exchange this d power from inside to the outside because it's a pullback. Okay, now you can use this identity and compute this as psi I minus the pullback of psi I times the rest. But we know what this is. This is exactly the correction. So now we can substitute the correction. Okay, but now we can reason as per usual with dimensional spaces. We know that this has 2 components. So this is more or less the product of 2 moduli spaces. On this right-hand side, we have M03 bar, so modular space of genus 0, because this is a rational component, with 3 special points, the point I, the point n plus 1, and this node. And in particular, the dimension of this modular space is 0, so this is a point. And then all of the rest you have on this side. But you know that now if you're putting psi class here, psi class has cohomological degree 1. But now you're trying to intersect the class that has cohomological complex degree 1 on a space that has dimension 0. So you're going to fail. I mean, this is just 0. It's going to give you nothing, right? If you put a psi class here. So you can't put, I mean, what I'm saying is that this is a proof of the fact that this divisor multiplied by any powers of psi class, in particular psi to the power psi I to the power d minus 1, is going to be 0. So this term does not contribute at all, so you can just discard it. But the next one is going to be psi I to the power d minus 2. And as long as d is at least 3, this is also going to vanish, and so on. So you can continue this principle until, I mean, you prove that all of them is going to vanish, except for the ones that do not have positive powers of psi I. So you end up with just you know, your divisor times the pullback of psi I to the power d minus 1. Okay, but what is the intersection between this divisor and the pullback of psi I to the power d minus 1? Well, of course, now you want to use the projection formula because you want to get rid of this. So projection formula get rid of this, but now the price to pay is to push forward this guy here along with forgetful map that forgets this n+1 mark point. This is a very good exercise because now we're putting together all of the things that we've seen before. If you're forgetting this n+1 mark point, then this component becomes unstable, right? And you don't want that, so you want to take the stabilization of this curve. Stabilization of this curve, if you remember, the way to fix that, the way to cure this instability was to shrink completely this rational component and to plug this ith mark point here on the node. So now this becomes just a fundamental class of mgn bar, not mgn+1 bar, but mgn bar. And now you got rid of this guy, so you just have psi I to the power d minus 1. And that's exactly the formula that you want. So you would get that this guy, this initial integral, you're now express it like that. And now you're using again the fact that if you intersect, if you remember, if you're intersecting a divisor with itself, sorry, not with itself, here you have I and here you have J. But of course, this is going to be 0, why? Because if you remember how to intersect divisors, you have here I and J. Here you have a node that separates I and n+1 from the others. And here you have a node that separates J and n+1 from the others. So now you would have two nodes, one. So you would need to isolate n+1 and put I and J. So you want to insert another node in this component and another node in this component, but that's impossible because here you already have M03 bar, and here you already have M03 bar. So you cannot split M03 bar. It's already like barely stable. If you insert another node, it will become unstable for sure. So the intersection between these two things is just 0. So now if you have the product here, I goes from 1 to n of these guys, you see that whenever you have this term here, and you try to intersect with some other term, it will fail. I mean, meaning that the summand will just return you 0. So you can only have one of these guys at a time, okay? And if you have only one of these guys at a time, if you only have one of these guys at a time, then you can just split your integral into the sum of the product of the pullbacks. But again, the product of the pullbacks is the pullback of the product. And because here you have the integral of the pullback, this will vanish for dimension reason, because think about it, the pullback, as we stated, preserves the homological degree, but now you are landing on a moduli space that has a different degree because you're adding a mark point, so the dimension goes up by 1, but the degree does not. Therefore, the degree does not match the dimension anymore. And so this term will just vanish. So you only remain with this term, and now you use projection formula. So again, you marry those two pullbacks, and you take the pullback of the product of all j's, which are different from I, of this guy times psi I to the power d I minus 1. But now this does not vanish because it's not a pure pullback. It's a pullback of something times something else. Now you can use projection formula. You get rid of the pullback. You pay the price of adding a push forward. The push forward of this, as we said before, by stabilization, you're forgetting this n+1 mark point. The point I goes here. This becomes the fundamental class of MGN bar. So this is now 1. This is equal to 1. So you can forget about it. And forgetting about it, you got exactly the right thing. And you're still summing over I, and you have your answer. So I think this is a very good moment to have a break. Okay, so let me just... I should also, I think, just change a little bit the way the... Okay, so we had a look at the proof of a string equation, and This is the statement that we want to prove. And then now we have all the steps aligned. Now in a vertical alignment is better. And then we saw that most of these terms are equal to 0, and therefore we can eventually reach the statement that we like. Okay, and the same thing you can do with the dilaton equation as well, applying more or less the same tricks. So it's the same idea. You start with the integral of mgn plus 1 bar. And let me remind you that in order to apply dilaton equation, you need a psi class to the power 1. For a string, you need a psi class to the power 0. For a dilaton, psi class to the power 1. And then for the following, Virasoro constraints would be some psi class to the power 2. Okay. So here we have any monomial that you like, psi 1 to the power d1, psi n to the power dn, and then psi n plus 1 to the power 1. I mean, by convention, is the last psi class to be to the power 1, but of course it doesn't matter. Like, you could apply it if psi 3 is to the power 1, of course. And then you need that the sum of the di's plus 1 is equal to 3g minus 3 plus n plus 1. So of course you can simplify this one and say that now the sum of the di's should be equal to 3g minus 3 plus n. So by the same argument as before, you can write now this down as mg n plus 1 bar, and you have the product over I of this guy over here that we derived from taking the psi classes pullback, if you remember. And you have a pullback of psi I to the power di plus this divisor that comes from the correction of the pullback of psi class, times again the pullback with respect to pi of this guy. But here you have di minus 1. And everything now multiplies psi n plus 1 to the power 1. Okay, so now again, let us observe that this divisor over here for a certain I, when you intersect it with the same divisor but for some other j that is not equal to I, their intersection is 0. So you cannot afford like multiplying this guy more than once, or if you do, then it will just vanish. So basically, out of this product, you would only have stuff that contributes that is of the form either this guy, you take it n minus 1 times, and then you take 1 time this guy over here, in all possible ways. So you would need to sum over I of doing that. Or the other option is that now you take only pure pullbacks from here. Okay, and in the string equation proof, we have seen that if you only take those terms for all I, then the result just vanishes because it's a pure pullback. And when you integrate a pure pullback, it will automatically vanish for dimension reasons. So you cannot take those guys in the string equation. But you do want to take one of these guys because that would ensure that the result of that summand is not a pure pullback, and therefore it does not immediately vanish, and then you discover that it actually does not vanish at all. But in the proof of the dilaton equation, now this vanishing swaps. So what used to be vanishing before, because it was a pure pullback, now if you only take those guys, it's not a pure pullback any longer, because you still have this psi n plus 1 to the power 1, which is not a pullback. So now if you take the product over all I of this term over here, the first one, times this psi, is not a pure pullback. So it doesn't have to vanish. Maybe it will vanish, maybe it will not, but it doesn't automatically vanish. And in fact, you discover that it will not vanish at all. Whereas now, if you take this divisor, you know that you cannot take that more than once because it will vanish. But you think that you maybe can take it once. So for one I, you choose this summon, and for the other ones, you choose that summon. No? When you have products of sums, you know that you can either like products of sum of two things. It means that for every summoned, you have to pick whether you want the first one or the second one for every I. So now if you take this one once, it will also not give you anything sensible because now you're intersecting this divisor with psi n plus 1 to the power 1. And now, as we noticed earlier, this component over here is a rational component with 3 special points, 1 node and 2 mark points. So the moduli space on this component is M03 bar, which is a point and has dimension 0. But now you want me to intersect this guy with a cohomological class of degree 1. So I cannot intersect something of degree 1 on a space of degree 0. It will just vanish. So I cannot afford to select this second term for any summand at all. Like, so this term will just not contribute in the D-Latin equation, whereas in the string it was crucial. So let us forget about this. It will just give us a 0, so we can completely erase it. So now the answer is just the product of the pullbacks of these guys times this psi class. But the product of pullbacks is the pullback of the products. And now you get the integral of the pullback of the product times this psi n plus 1 to the power 1. Now this guy is perfect to be is perfect for the application of the projection formula, because now you have the integral over mg n plus 1 bar of a pullback of something times something else. Now, as you apply the pullback, the projection formula, you will get rid of this plus 1, so you will land in mg n bar. And now the rule is that what used to be pullback, now it's not pullback anymore. And what used to be free of pullbacks and push forwards now gets push forwarded. So now this guy is exactly what you want. And here you have the push forward of psi n plus 1 of 1. But this is exactly by definition kappa 0. Okay. And kappa 0 now is a number, it's not a class. So you can even bring it outside of the integral if you want. And what does it mean kappa 0? Okay, let us have a look at what does it mean kappa 0. The idea is to integrating the tangent bundle. That integrating the tangent bundle gives the Euler characteristic. So if you're familiar with this principle, I mean, you would recognize the Gauss-Bonnet theorem. It's basically Gauss-Bonnet theorem tells you that if you have a k-dimensional manifold M, and you want to compute its Euler characteristic, this will be up to some sign that depends on the dimension. It will be the integral over your manifold, sometimes compactified, of what you would take the top Chern class. So because this is of dimension k, you need to take the top Chern class, so the kth Chern class of what? You have to take the kth Chern class of these differential forms, so omega 1, over n bar. But now you shift that by log d, where d is the boundary of M. So you start with something open. Now you had to add the boundary d in order to compactify it. And you have to shift by log d of this shift, and then you compute the top Chern class of that. So this might seem a little bit complicated, but now we can adapt it to our case where k is just equal to 1. So you want to compute the Euler characteristic of the curve. And you can compute that by taking minus to the power 1. And now you're integrating over the curve the first Chern class of the cotangent bundle. Well, here there is a bar of the closure. And then now you have to shift by the boundary. But the boundary is just this pi. So I'm taking the log of that just amounts to shift this guy by the sum of this divisor, and this divisor will be just the sum of the pi's times 1, so multiplicity 1 for each of the pi's. And now, since as we've seen, the universal curve over virgin bar is the same thing as mgn plus 1, turns out that k0 is the degree of this guy, because when you compute the first Chern class, you have the zeros minus the poles counted with multiplicity. And so now this gives you the Euler characteristic of the curve minus n points, because this is C open, so you don't have the boundary here. So the Euler characteristic is of a curve of genus G, of course, is 2 minus 2G. But now because you removed n points, it's 2 minus 2G minus n. And because of this extra minus sign, you would have an extra minus sign. And so now kappa 0 would be the 2G minus 2 plus n, exactly as you expect. So now this kappa 0 here is 2 minus 2 minus 2g minus 2 plus n. And this number would just give you exactly the D-Latin equation. I don't know where we wrote the D-Latin equation. probably in the previous lecture, but somehow like the Latam equation is just that this left-hand side over here with psi to the power 1 is just equal to this integral over here where gn plus 1 became gn. And now you have the same monomial, but you don't have this guy over here. This guy turned into 2g minus 2 plus n. Okay, and so now you can, I mean, we proved geometrically both the string and the Dilaton equation, which are very important equations. And they are also the first two equations of the Virasoro equations. I don't know if I ever seen the proof of other Virasoro constraints with geometry. But that's usually not how people prove them. Anyways, the first two are quite, I think, informative to prove by hand using geometry, because then you really are forced to play with these tricks that are useful in many ways. Okay, so this basically ends the part, strictly speaking, on moduli space of curves. And now I just wanted to motivate a little bit moduli space of curves with some application. And the application that I have in mind is some numbers that I like very much, which are the Hurwitz numbers. And Hurwitz numbers indeed pop out in many different contexts, including Kolmogorov theory, topological string theory, and especially the story of the mirror symmetry for Calabi-Yau, toric Calabi-Yau threefolds. So maybe let me speak about the motivation, since last time you told me that you enjoyed the motivation that I gave at the beginning. So maybe I can speak a little bit about the global picture a bit more. So the Hurwitz numbers were studied just for pure enumerative algebraic geometric reasons at the beginning. They were introduced by Hurwitz himself. And basically, Hurwitz numbers are counting coverings of Riemann surfaces. So basically, Hurwitz numbers are just the answer to the question, how many Riemann surfaces coverings are there with the condition that blah, 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 and you only have this amount of ramification profiles and this amount of branch points, and that genus and that degree of the cover, right? So if you fix enough data, then you can ask the question, how many Riemann surfaces coverings are there? The given degree, given genus upstairs, given genus downstairs, and given branch points, fixed branch points, and the ramification points are also fixed and of given ramification index or profile. And the answer is generally not 0 or 1. The answer is in general like some interesting number. And usually when you count stuff in enumerative algebraic geometry, you count that up to automorphisms. And also, I mean, you don't count honest individual coverings, but you count them as isomorphism classes of coverings. But furthermore, every time that there is a cover or a class that is more symmetric than others, now you divide by the amount of automorphisms. So if there is a class of automorphisms of coverings that has automorphism group of cardinality 2, then you would count that equivalence class weighted by a half. That's how you want to do things. And this is a general principle in combinatorics and enumerative geometry. And whenever you do things this way, I mean, the generating series turns out to be nice. If you don't do this, then, I mean, usually it's not nice. So that's something just people learn to do it whenever you define a new enumerative problem. And the Hurwitz numbers don't make an exception. So the more these objects are symmetric, the more you divide. And then you just sum all of them up, meaning that the total sum of these fractions, because each of them will be a fraction then, will be either an integer or a fraction, but you sum them all up and you will get a rational number. So Hurwitz numbers are rational numbers. They are rational numbers and they are positive because you're counting the number of coverings. So it will be a positive number. And then you just at most divide by the cardinality of the automorphisms. So you have positive rational numbers. And there's this beautiful story about remodeling the B model. There's this beautiful story about mirror symmetry. In mirror symmetry, probably the experts in this audience, you have this A model and this B model, and then you have a way to pass from the A model to the B model, taking a mirror of blah, blah, blah. But the main point is that A model is more, the A model in general is, how do I say? The A model usually concerns more enumerative algebraic geometry, and the B model usually concerns more some differential aspect, like spectral curves or some matrix model or some differential geometric object, some curve or some partition function of some object. And somehow like the game is to find the right object that corresponds to the enumerative problem in the A model. And then there was this big paper that people usually refer to BKMP because it's the acronym of the four authors. So Bouchard, Clem, Marigno, and Pasquetti, BKMP. And the paper is called Modeling the B model. And there was a big conjecture there, and the big conjecture stated that if you have a toric Calabi-Yau threefold, which of course is a central object in mirror symmetry, toric Calabi-Yau threefold, you know that you can always construct it with building blocks. When you look for the partition function, you can always construct the partition function by gluing partition functions of these basic building blocks, which is the topological vertex, which is something that has valency 3, and then you start like gluing other valency 3 thingies, and they become sort of a complicated graph where you have more and more vertices, but they're all trivalent. And depending on how you glue them, you have a certain genus and so on. And the main point is that there was this procedure called topological recursion by Enard and Orantan that we mentioned several times. And somehow the big conjecture was that if you take any Calabi-Yau Calabi-Yau threefold and you look at this object that you're constructing this way, then you can interpret this object as a spectral curve for topological recursion. So as the initial data of the topological recursion, meaning the data that you would need to then run the algorithm, and this algorithm would start spitting out some numbers. And now you say that these numbers are exactly like the correlators of your Calabi-Yau threefold, like the Gomovitin invariant or whatever you like. Okay, and so this conjecture was then proved. But out of this conjecture, there was a spin-off. There was a spin-off by two of the four authors, so just Bouchard and Marigno together. They made a spin-off on the topological vertex. So just on the mirror of C3. But this topological vertex, you want to think of it as framed. Framed just means that you have some extra parameter. And now in the limit where this extra parameter is sent to infinity, you should recover some well-known numbers. And these numbers are Hurwitz numbers. So basically out of this big conjecture, the remodeling the B model conjecture, there was a spin-off conjecture. There was the Bouchard-Marigno conjecture, and the Bouchard-Marigno conjecture stated that if you take the spectral curve, topological recursion spectral curve for the topological vertex, you're going to get Hurwitz numbers out of it. And then this conjecture was also proved now in many ways. So this is the motivation for me of Hurwitz numbers in mirror symmetry. And the other motivation is due to this famous trilogy of Okunkov and Pandaripande. When they solved in 2006, around 2006, they wrote 3 papers. And they solved the whole Gromov-Witten theory of algebraic smooth curves. And they also use Hurwitz numbers there. Because Gromov-Witten theory is somehow like too complicated, but Hurwitz numbers are just simple enough that you can compute them and handle them. And now you can transition what you learned and the theorems on Hurwitz numbers, you can now somehow translate them, or you can transition those results. You can move them from Hurwitz theory to Gromov-Witten theory. And I mean, yeah, this trilogy was also a very big deal in the community. And so in both of these examples, Hurwitz numbers played a key role. You can think of Hurwitz numbers as the easiest toy model that is not trivial. Still like very interesting and very rich in combinatorics, in geometry, in physics. There's a lot of physics behind it. So I love Hurwitz numbers, and when you have a conjecture, sometimes you can test it in Hurwitz theory, and then you can export it on the context that you want to work on. So it's a very rich world and has been very useful to do other things. And in particular, something that I wanted to show you is this beautiful ELSB formula. So, okay, let me stress, since I believe that in this course, there are many people interested in application to theoretical physics, I wanted to connect Hurwitz theory to mirror symmetry and also to Gromov-Witten theory of algebraic curves. But on the other hand, I mean, Hurwitz numbers have been studied by algebraic geometers and geometers for like much longer amount of time, like more than like 150 years. So somehow geometers don't need an extra motivation from physics to study Hurwitz numbers. They can be interesting per se. And also turns out that they play a very nice role in the intersection theory of moduli space of curves as well. So this is one of the most beautiful results concerning this connection. This result is called the LSV formula. And again, like many of the things that we mentioned in this course are just the tip of the iceberg. I mean, I don't have the time to show you everything that is known so far because it's just too much. But it's very interesting for me to show you the starting point. So when we talked about Witten conjecture and Kontsevich theorem, we also mentioned that there was the tip of the iceberg between a long, by now, like kind of well-explored connection between integrable systems on one side and algebraic geometry. And when you intersect some cohomological field theory or some interesting cohomological class, you get some interesting list of PDEs on the other side. So that was also like the tip of the iceberg of a very deep theory by now, and which is still going. Like it's very much hot topic of research now. I mean, so I'm going to this conference in Australia tomorrow, and this will be one of the points under discussion. And this formula as well, the formula that I'm about to describe, this ELSV formula, is also tip of the iceberg, as a connection between Hurwitz theory and moduli space of curves. Because, I mean, on the left-hand side, you have Hurwitz theory, on the right-hand side, you have integrals over MGM bar. But again, I mean, I'll show you that you have some particular class there. But again, if you change the class over the MGM bar, the homology, MGM bar, you do have I mean, this connection doesn't stop. We have many other instances of this type of formula where on one side you're integrating over MGM bar some particular class, and on the other side of the equation you have some particular Hurwitz number. You can change your Hurwitz number. You have many types of Hurwitz numbers, and you have many types of cohomological classes of interest over MGM bar. And just so turns out that there is an extension of the ELSB formula that is connecting them. So this formula is not one formula. This formula is the first formula. And after this one, we had discovered many other the community has discovered many other ELSV type formula. This is also, I mean, related to my work, but that's not so important. I mean, I just wanted to say that you don't have to think of ELSV formula as just one instance. It's a very rich world. And I think by now we have, I don't know exactly how to count, maybe like 7, I don't know, 6, 7, right? Depending on how you count them, but there's more and people are trying to get more out of Hurwitz's theorem. Or to generalize it so to understand something like deeper behind this. Actually, for me, what is interesting about this formula, other than the connection, is also how people, the methods that people use to prove them. Initially, the first proof of this formula was completely from algebraic geometry. Then there is a beautiful paper by Kichumeli Saliu that also gave a course at Latam, I think, on modular space of stable curves. Well, modular space of stable maps, I think, and Gomulkant here. I think in her course, she also describes in detail the story concerning the solution of the BKMP conjecture, because, I mean, she was one of the 3 authors in the paper that solved the conjecture. And well, she also wrote an expository paper a research paper on another way to prove this formula via virtual localization that I would highly recommend. And by now we have many other proofs of this formula. One of the proofs is by topological recursion, which is very nice. And also you can use this Telemann-Giventhal classification of cohomological field theories, which is also like per se a very, very interesting result. And I find this ELSV formula a very nice application of the Giventhal-Telemann theory. But anyways, like the formula has been proved in many ways that are very different from each other. That's my point. And also we have many other types of this instance where you connect Hurwitz's theory and modular space of curves. But let us have just a quick look at what the actual formula, the basic ones. This is the first one, the original ELSB formula. So again, ELSB is itself also an acronym of the 4 authors. So the 4 authors are Ekedal, Landau, Shapiro, and Weinstein. And this formula is from the 1999, I think, 2000, maybe the year of publication is 2000. It's published on Invenciones. And here on the left-hand side, you have the Hurwitz number, meaning like you're counting how many covers you have over P1. So you have genus 0 downstairs and some genus G upstairs. And you require that you only have like simple branch points all over. This is degree D. And but you have one special point over 0. You can imagine this is 0. And despite having only simple ramifications everywhere else, you just have one single ramification profile over 0. So these are the pre-images of 0. And here you have ramification index given by mu1, mu2, mu3 up to mu(n), where, of course, if you sum, these are all integer positive numbers. And if you sum them up, you get the degree of the cover, of course. And now, like an intelligent question is, if you consider this not just as a number, but as a function of the mu i's, so as a function of the ramification indices, this turns out to be a very interesting object, and it splits into 2 very different factors. The first factor is just a number. I mean, it's a function of the mu i's, but it's just a number if the mu i's are numbers. And it's something that is highly not polynomial. So if you look at it, you just have the product over I from 1 to n. Here you have mu I to the power mu I divided by mu I factorial. So there's sort of very highly not polynomial in the mu i's, right? And this is very interesting. And if you know a little bit about virtual localization, you would recognize that from virtual localization of modular space of stable maps and so on, you often get terms of this shape. And indeed, I mean, indeed, they come from there. I mean, depending on how you prove it. If you prove this formula by virtual localization, they do come from there. But if you prove it with topological recursion, they also come from topological recursion in a completely different way. So it's very interesting. But this is a number whenever the mu i's are numbers. Whereas this piece over here is the integral over a modular space of curves, and you have some cohomology class here. Some cohomology, so you recognize immediately the psi classes here, and they are paired with the mu i's. So now the mu i's multiply psi classes. So it's very beautiful. And this denominator means that you expand in geometric series. So you can think of these as just geometric series expansion. And of course, you don't need a whole series because the geometric series would be cut at the dimension of the space, which is 3g minus 3 plus n. So they're in fact polynomials, right? So polynomials in the mu i's, clearly, very clearly polynomials of degree 3g minus 3 plus n. And here you have the total Chern class of the dual of the Hodge bundle. So this is exactly what we called before big lambda of minus 1. So here you really have like 1 minus lambda 1 plus lambda 2 minus lambda 3, and so on, up to minus 1 to the power g times lambda g. So this polynomial in the mu i's is not homogeneous of degree 3g minus 3 plus n, but is indeed a polynomial that is top degree is 3g minus 3 plus n, and bottom degree it's not 0, but is 2g minus 2 plus n, because this guy is only polynomial of degree g in the cohomological degree. So you don't have all of the degrees in this polynomial. You have very specific degrees. So for me, this is a beautiful formula per se, because so this is a classical problem in classical geometry problem. No? How many Riemann surfaces coverings with these conditions are there? And now we discover that the answer is the product between something that is highly not polynomial in the mu i's times something that is very obviously a polynomial in the mu i's. But here, this is an intersection number of the modular space of curves. So it's very, very beautiful formula. So this is what I wanted to show you. And then, I mean, I could give an entire course on Hurwitz numbers. In fact, I did several times. Here I have notes of basically an entire course on Hurwitz numbers, but this is not the topic of this course, so I don't want to give too many details. But somehow the Hurwitz numbers are a beautiful world. You start with this geometric definition. You're counting covers, but this is also very hard to use in practice. So you can restate that in terms of representation theory, and then you can restate that in terms of character formula over the symmetric group. And this is known as Burnside formula or Frobenius theorem. And then you can restate that in terms of a vacuum expectation value of some operator over the Fock space. And well, this is the link with physics. And then you have a link with tropical geometry. I mean, it's such a rich and interesting world, but I mean, I don't want to focus too much on that. I just wanted to give it as a motivation for modular space of curves. And then, of course, counting Hurwitz numbers is complicated, but people came up with all sorts of recursions. And one of these recursions is the famous cut and join recursion. And then you can use topological recursion. And then here I describe a little bit some Hurwitz numbers. Let me just go, I mean, very, very fast. This is not something that I want to introduce. Also, I don't particularly like the fact that I use the dark background. I would probably have to rewrite all of that with a white background so that it's more visible. Sorry, let me just scroll to the end. This is the proof of the Cut-and-Join equation. And the degeneration formula of Hurwitz numbers. Maybe I can just finish with Cut-and-Join equation. Yeah, which is this theorem over here. So one of the recursions that is usually used to count Hurwitz numbers is this cut and join equation. And indeed, it's called cut and join equation because you actually cut and join something, and you cut and join graphs that represent this Riemann-Hurwitz coverings. So you can restate Riemann-Hurwitz coverings as purely combinatorial objects because of this theorem, existence theorem by Riemann. And now they become constellations. They become sort of purely combinatorial objects that are labeled by graphs, they're encoded by graphs. And now you can cut or join some edge of this graph, and this gives you some recursion. You give some bijective combinatorial argument, and this gives you this equation, where this edge with this bullet is just the generating series of Hurwitz numbers, possibly disconnected. This is what this bullet means. And now you have several variables. The variable u, for example, keeps track of the Euler characteristic of the surface. And the variables p, instead, they have to deal with, they have to do with the ramification profiles, these mu i's that you've seen before. So you have something like p mu1, p mu2, p mu3. So now basically this equation tells you that if you are removing one simple branch point and you're decreasing the Euler characteristic of the surface, this is the same thing as taking 1/2 times all of the ways of adding two ramification profiles with ramification index I and j, but then you need to remove one that has ramification profile I plus j. So when you multiply, you remove it. When you differentiate, you add it. It looks like exactly the opposite that you're meant to do, but this is how differential equation work. And then you weight it with some stuff. And then plus, meaning that you have two different cases. Whenever you have plus, means that you either do something or you do something else. And you add a ramification profile with index I plus j, but you remove instead ramification points with index I and j, and you multiply by this prefactor. And so with this equation, you can compute Hurwitz numbers. And actually, yeah, you have all sorts of recursions. This is one of the recursions that is very handy to use. You have topological recursion, and you also have connecting back. So at the end of the course, we go back to the very first equation of the course. If you remember Witten conjecture and Kontsevich solution, the conjecture was that the generating series of the integrals of psi classes satisfy the KdV equation, and therefore the entire KdV integrable hierarchy. So this infinite list of PDEs in infinitely many variables. And Hurwitz numbers have very, very similar property. The generating series of Hurwitz numbers indeed does satisfy an infinite list of PDEs and in infinitely many variables, which is an integrable hierarchy, but it's not the same list as psi classes. It's slightly different. It's not KdV. It's called KP instead of KdV. So KdV was standing for Korteweg de Vries. And KP is very well connected with KdV. In fact, KdV is a reduction of KP. So KP depends on times that are, so you have this set of times that can be labeled by natural numbers. And whenever you can prove that the equation does not depend on the odd times, or it only depends on the odd times, then you get KdV out of KP. So KdV is just a reduction in the sense that it's the same as KP, but it does not depend on half of the times. And so indeed, the generating series of Hurwitz numbers does not behave, has some similarity with the generating series of psi classes. And this is also not a complete surprise because of Hielsv formula. And that, I think, should conclude the mini course.